Hi everyone, today we are covering explicit congestion notification (ECN), a way for the network to signal congestion without waiting for the packet loss. In classic TCP, the usual congestion signal is a drop, but drops are expensive. They trigger retransmissions and sometimes timeouts, and they often happen only after queues have grown, which increases delay. The big idea we will build toward is, if a router can see congestion building, why not warn endpoints early by marking packets instead of dropping them? So first, let's recap Reno quickly, because ECN mostly changes the signal Reno reacts to. Here is a quick TCP Reno recap. Reno adjusts the congestion window using additive increase, multiplicative decrease. The congestion window grows, and when congestion is detected, the window backs off. And the key point here is Reno infers congestion from loss. It reacts to either 3 duplicate acts or a retransmission timeout. But loss is a late signal and it's disruptive. And that's the motivation for ECN. Can we signal congestion before we hit drops? To make ECN possible, routers must be able to warn the endpoints about ongoing congestion. This is where active queue management style thinking comes in. Routers can detect early congestion before the buffer overflows. For example, a rising queue possibly indicates future congestion. So instead of wait until the queue is full and then drop the packets, the router can sometimes mark packets to warn endpoints early. We will talk about the algorithms in detail later. That's the intuition. Early warning helps keep queues shorter, so the endpoints get lower delay, and they can avoid turning congestion signals into retransmissions.
Hello. Before we continue our breakdown of ECN, I wanted to discuss some concepts that are foundational to ECN's algorithm. One concept being random early detection. Random early detection is a form of active queue management. Implemented in the routers, it detects early signs of congestion and notifies the end host so that it can lower transmission rates before overflow. Furthermore, it can also be used to mitigate the amount of packets dropped in cases of congestion and overflow. In random early detection, you monitor the moving average of the queue length, or the buffer occupancy as you can also call it, and set 2 thresholds: the minimum threshold and the maximum threshold. These thresholds are set to gauge how much congestion you'd want in the system before you start reporting or notifying the end host, as well as dropping packets. If the queue length is below the minimum threshold, then all packets are admitted into the queue. If the queue length is above the maximum threshold, then all packets are dropped. If the queue length is in between the 2 thresholds, then the packets are dropped probabilistically based off a linearly increasing function. Please note that the queue limit and these thresholds ideally do not reach but simply approach the maximum capacity limits of the system. A variant of random early detection is random early marking. In random early marking, rather than dropping packets, you simply mark said packets, and in this way, the receiver still receives said packets and note their transfer is still made. The receiver, however, still notifies the host of the marked packets, and in this way, the state of congestion is communicated and can be measured from the fraction of marked packets. ECN uses marks rather than drops for the sake of completing transfers, while also having the benefit of the notification. Other variants and enhancements of random early detection include adaptive random early detection, which adjusts the max drop probability to maintain a buffer occupancy or queue length. Weighted random early detection, which gives or applies different drop probabilities to different packets based off priority and classification. And ECN. Do note that random early marking can also be applied to each of these variants, And ECN, as an enhancement, uses those marked packets instead of dropping them, and it also signals congestion rather than just applying a slowdown to the system. Here's an example of an ECN response. You see here we have 3 criteria, 2 of which being very similar to TCP Reno, where you have on timeout and 3 dupbacks as well as congestion avoidance. However, there is a third criteria. When an ACK with ECN is received, reduce the steady state threshold and congestion window by beta. This beta denotes the reduction parameter, and it's usually a percent decrease. For example, 0.2, which would reduce the steady state threshold and congestion window by 0.2. Secondly, there's also a set increase slope to alpha. This alpha value is usually less than 1, so it's usually less than the value that you would reset it to on timeouts and on duplex. Please note that this increased slope does reset to 1 on timeouts and on duplex, and this affects the congestion avoidance increase every time you have a finished or every time you have a received ACK. Anyway, this is just an example of an ECN response. We're going to go break down into the ECN goal and how ECN actually touches the bits.
Here we talk about the goals of ECN. Floyd's early ECN paper introduced the idea to incorporate ECN into TCP, and this RFC document specifies an Internet Standards Track protocol about ECN for IP and TCP. ECN goals are basically notifying endpoints of congestion without requiring loss, especially when congestion is predictable and developing. If you can replace some drops with marks, you reduce unnecessary retransmissions and timeouts, and that often reduces delay too. 2 more goals matter a lot for stability and deployment. The first one is to make the sender's response to be Reno-like in order to preserve fairness. The key design choice is that an ECN mark should be treated as a real congestion event, similar in spirit to how Reno reacts to loss. That matters for fairness. ECN-capable flows shouldn't become more aggressive just because they avoid drops. The second is don't overreact. If many packets are marked during one congestion episode, the sender shouldn't cut congestion window repeatedly in the same round-trip time. Now let's map this onto actual header bits. TCP adds 2 key flags for ECN feedback. The first one is ECN echo. It is set by the receiver to tell the sender I saw congestion marking. And the second is CWR, congestion window reduced. It is set by the sender to say, okay, I see your congestion marking and I have already reduced my congestion window. So ECE is the receiver to sender echo and CWR is the sender to receiver acknowledgement that it backs off. At the IP layer, ECN is a 2-bit field with 4 code points shown in the figure. Here in the figure, ECT means ECN capable transport and CE means congestion experienced. So the sender will use this field to indicate whether it is sending ECN-capable packets, and the routers can flip those bits on the packets to indicate congestion. ECN requires negotiation because it only works if both endpoints agree. So this RFC documents define negotiation in the TCP three-way handshake. In SYN, the initiator raises ECE plus CWR to request ECN, and in SYN-ACK, the other side raises ECE to accept, and they shouldn't mark SYN or SYN-ACK as ECT in IP header. After negotiation, let's see what happens at runtime. The figure here shows the runtime loop. The sender will set packet's IP header as ECT. Router will check whether it is ECN capable, and if it is and there is congestion going on, router marks CE in the IP header of the packets instead of dropping it. Receiver sees CE and then sets ECE bit in the TCP header on X. Sender receives ECE, treats it as congestion, reduces the congestion window, and then sets CWR on the next new data packet. So in summary, the mark forward on IP, echo back in TCP, and sender backs off, all without requiring loss. Another critical stability problem is that one congestion episode can mark many packets. You don't want to cut congestion window several times on one round-trip time. So the desired behavior is, for many CE marks, only perform about one congestion window reduction per RTT, instead of one for each CE mark. In addition, the receiver keeps sending ECE until it sees CWR, which makes the signal robust even if X are lost, but the sender still limits its reduction. Regarding the benefits, ECN can give us lower delay, fewer drops, fewer retransmissions, and fewer timeouts, but it still requires end-to-end plus network support, and it cannot prevent drops under real overflow. And there's fairness problems that sender must actually respond to the marks.